Okay, right here got a little boost converter, good from about 4 to 40 volts. Got a little PWM board that was real nifty looking for real cheap. Adjust frequency, I believe up to 150 kilohertz, and duty cycle. So this all came together as I can just use a 4 volt or so battery bank, easily rechargeable, drive this boost converter to get anywhere from a 4 to 40 volt or so output, and I can also use this little board here to pulse modulate loads using this output from this converter through this little transistor. I'm just using a 2N3055 because I actually found that to be a little more effective than the MOSFETs I had on hand. So essentially what it boils down to here, I've got just regular my variable DC output, non-pulse modulated, and right here is the output that's ran through the transistor that is being controlled by this board here. And one of the things that I've always wanted to make, I just never got around to it, was just a cool little fan circuit that would spin at whatever RPMs it would spin, and then I always wanted to just build a little joule thief or something. Something like, some little guy like this that would put out enough light that I could also get to pulse at a low enough frequency, bright enough to where I could get the little effect to where, if that was the only light shining on this fan, then it would look like it was motionless even though it was spinning. So just kind of tinkering around, I was like, okay, well, let me see if I can get the output here to match that to get the same effect. And what I noticed was I thought a kind of a cool little way to visualize how the pulses work. And one thing I've noticed with joule thieves, they always kind of work for that application of with this little fan that I was talking about, because at those frequencies the duty cycle is very low. You've just got quick spikes, and it gives you a really good visual effect. Whereas in this case, so if I turn the circuit on, so we're at 86 hertz. I believe that's where it was at before. And let's just put the duty cycle up to about 60%. And this little strip here is damaged, so it'll come on at a low voltage. Let's see, it'll come on fully at about, there you go, about, let's just say 25 volts or so. You can see that's kind of fissioning with the camera. I can increase the frequency. This is what we're looking at across that LED. Got 60% duty cycle, about 91 hertz I've got coming from this board here. So that's about right. So what I'm going to do is I'm going to cut this light off and then cut the other light off. So this is going to be the only light shining, and I'm going to put it towards that fan, and I'm going to see if we can match the frequency. Alright, so now we've got only this light on in the room, shining at the fan. It's kind of dirty. Cut the fan on. Let that get up to whatever speed it's going to get to. And then I'm going to change the frequency. I know I need to lower it, but I'm going to drop the frequency until it looks like I'm matching the speed of this fan here. Now it's really hard to see on camera, but I'm fairly close to that fan speed. But the reason we're not able to see it is because of the duty cycle. So I'm going to drop the duty cycle. I'm just going to keep dropping the duty cycle. It's at about 50% now. Keep dropping it. as I'm dropping the duty cycle, the intensity of the light is decreasing, of course. So I'm going to drop it all the way down to 1, see if I can get it back up a little bit with the voltage. And now we're going to look at it again. And I'm going to adjust the frequency again. So now we're at a 1% duty cycle. We're at the, oh, you can't even see that, 1% duty cycle. That's the shortest amount of pulse that we could get. And I'm going to start increasing the frequency. Now it's kind of hard to tell, but now we're at a point where the fan is looking like it's barely moving. There we go. Right about there, it's looking like it's barely moving at all. This camera is, you know, it's also playing a role there. But we can see that at a 1% duty cycle, 86 hertz, now we've more or less matched the speed of this fan. And we can give it the appearance that it's increasing or decreasing speed. Now it's a lot slower. There we go. So the duty cycle is at 1%. And that's what's necessary to be able to see this effect as clearly as it is. Now I'm going to start increasing the duty cycle 1% at a time. See, the light's a little bit brighter. You can see the more I'm increasing the duty cycle, the blurrier the image of the fan blades become. Right? This is just because per pulse now you've got a longer on time. You've got these rotating fan blades that are moving at a certain speed. So the longer this light is on per pulse, the longer your eyes are going to notice a change in motion. Hence the blurriness. So when I decrease the duty cycle back down to about 2, now you can see the pulse is so fleeting that it's your eyes are not able to reference a change in motion as well. Bump it way up, and you know you can no longer see the effect. Even though we've more or less matched the frequency, you just can't tell. On time is too great. Here's another little more direct, simple way to visualize it. PWM duty cycle, I mean, I'm sure most people get it, but I never see it actually explained at really low frequencies. So right now, got a 25 volt output into this LED strip load, and it's being told to run at 1 hertz. And right now, we've got a 1% duty cycle. You can see across the screen here, we've got that little 1% duty cycle blip running across every 1 second. That's what we're looking at. Now, what's interesting about seeing this flash through this camera is it just looks weird. You know, it's almost like it's so quick you don't actually see any of the emitters lighting up, but you see just a mystical flash come from somewhere. That's that 1% duty cycle. So you can see if I increase the duty cycle, we're still at the same frequency. It's still blinking every 1 second. But now we're at a 10% duty cycle, and that little blip has gotten fatter, so it's on for a longer amount of time. Each time it blips every 1 second, and you can see it. Let's put it all the way up to 50 just for the reference. So now we're at 50%. Now you can see it's on for half of the second and off for half of the second. And So let's leave that at 50% and then increase the frequency. 2 hertz. Let's bring it up to 20 hertz. Hertz, 50%, and let's bump that all the way back down to 1%. Very fleeting. Let's put it as 10%, or 10 hertz, 1% duty cycle. I'm just gonna slowly increase the duty cycle. Makes more sense of what's going on. You've got an average voltage, an RMS voltage. Now let's go. Let's bring it. Let's put it back to 1 hertz. So you've got 25 volts or so across this load every second. Pyong, 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 pyong. Is it seeing 25 volts? What's that seeing? Well, the RMS, or the average, is not going to be anywhere near that 25 volts because of that fleeting pulse right there, that 1% duty cycle. But it's still receiving a 25 volt pulse throughout some period in time. Increase the duty cycle to 10%. Now your RMS voltage has increased a whole lot. You're still outputting 25 volts, but what this is averaging still nowhere near that. And that's not based upon the frequency, that's based upon the duty cycle. Bring it up to 20. Alright, now let's bring it all the way up to, let's bring it to 90. 1 hertz, 90% duty cycle. So now we're on 90% of the time, off 10% of the time, every 1 second. So whether this is a motor, or whatever load this is what is happening, but it's much easier to visualize and see through something like an LED. Alright, now we got an example using a small motor here. And this motor is being told to run at 1 hertz, 1% duty cycle, which is at around 10 volts. So you can see every second it's getting a jolt of 10 or so volts. So this is the equivalent of taking a, let's just say, a 9-volt battery, tapping it against the contacts every second. But that's where duty cycle comes in, because as your human fingers are tapping the contacts across the terminals, how long of a period over time are those terminals contacting with the battery as you brush it across with your hand? Is it a very fleeting contact, or as you're touching it, are you kind of holding them down for a little longer period of time? Well, that's what duty cycle is here. 1%, it's the shortest amount of time we can register here that it took for that metal on metal contact to provide that 10 volts. Pew, pew. So, without changing the frequency, bump it to 2% duty cycle. A little more of a ferocious pulse there. Now, as you can see, technically speaking, we're still driving this at around 10 volts. But since it's only at 1 hertz, we don't have a solid rotation, obviously. But the longer we leave that motor on for that second, or the longer we increase the on time of that motor every second that it does pulse, you can see it's got more of a oomph to it. Now every time your battery is making contact to the terminals, you're holding it down for a little bit longer each time. Still, this guy is not getting the momentum to maintain a constant rotation. Let's try around 20% duty cycle. Let's go up to 31, let's go up to 40. So let's see what it does at a 50% duty cycle. And let's increase the frequency to, let's cut it off. Let's bring the frequency to 5 hertz, 50% duty cycle. So you see, now that we've increased the frequency, during each pulse, the duration has become shorter per pulse. Ring, 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 ring. Whereas opposed to at 1 hertz, ring, ring, the on time is much longer through time. Just because we've got more time to work with now. Bring it up back to 5. Let's do 10. So we've got a continuously spinning motor now, but it's horrendously inconsistent because it's only moving at 10 hertz. Let's bring that, well, you know what? First, let's bump the supply down closer to around 5 volts. And then let's bring it to a more reasonable frequency than a motor would want. Let's bring it to about 150 hertz or say. About, arbitrarily 150. There you go. Let's bring it back down to 1% duty cycle. At 150 hertz, 1% duty cycle. Now we see it's pretty much doing nothing. It's got no rotation. However, I can hear a slight buzz in the motor. And that's simply because now we're at such a high frequency that little 1% blip throughout each pulse is nowhere near enough, has nowhere near enough current in it to really get this rotor moving. It's really just going to start ringing the coil like it's doing here. I can turn the voltage up. The ringing becomes more intense. But that's about it. Now maybe I could give it a kickstart. Sometimes you can. Not at a 1% duty cycle. Let's try 10%. It almost wants to go 10%. And it's just barely going at 10%. Now that we have it just barely going at 10%, let's see what happens when we change the frequency. Let's lower it. now we've stopped. It's just the physics of this particular motor. There we go. Let's get it going again. Now let's increase the duty cycle. Now let's bring that up to about 20 and get it going again. Alright. So we got her going again. Good speed. We need to back that voltage down. So we're going. 140 hertz. Let's start picking up the speed. So are we raising the voltage? No. I'm not raising the voltage now. We've just met a certain set of parameters here as far as frequency, this motor, what it takes to get it rotating, and now the on time being increased is also gradually increasing the speed of the motor here. So now we're about at 100%. Boom, we're at max. 100%, 8 volts, 140 hertz. I'm just going to go sweep up and down frequencies just to see what it does. We're at 5K. 95% duty cycle, 5 kilohertz. RPMs are increasing. It's about where they're maxing out. Alright, that's about it. Let's go back down. Huge decrease in speed. Had a dip there between about 3 and 5 kilohertz. We're leveling out. You see, with this motor, no significant change till you really get way up to the much higher frequencies. But this is given that the motor's already going. Let's bring it all the way back up to what it was like in the much higher frequencies. Wait for it to shift in a RPM here. Boom, so it likes these higher frequencies. Alright, let's cut it back off. And see what it does when we cut it back on. Oh, there you go. Came back on, no problem. Now let's bring it down. And we've stopped. We've already stopped. We have to get way up there in the duty cycle at that frequency to get it going. So right around here, we're going real slow. So, back down on the frequencies we go here. We shoot way up. Way up. Way up. See, that higher duty cycle, longer on time, is being allowed more juice, more oomph per pulse now because there's less pulses over time. It's what this particular motor wants. Some interesting ringing going on in there too, some sounds I can hear. So we're back in the more motor reasonable frequencies. There we go. Leave it right about there. And there you go. You can bring the duty cycle all the way down now to a more reasonable level. We have a wider range of control given this motor here. Right around there, it stopped.